Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to give you a working definition for the cohomology of coherent sheaves on a projective curve. Okay, so we'll work slightly more generally in this video. So let X here denote some quasi-projective curve over an algebraically closed field K. So that's some quasi-projective variety, which is one-dimensional. Okay, so to set up the definition that I want to give here, I want to use the following rather useful and interesting fact. Okay, so that is that given any such X, you can obtain an open affine cover which has two open sets U0 and U1. So X equals U0 union U1, and these are open and they're also affine varieties. So let's just see roughly why it's true. I don't want to prove this fact for you, but it's quite easy to understand why it ought to be true. So the simplest case to have a look at this and see how it arises is when you have X equals P1. And in that case, we know that this is just the union of two affine lines. Okay, you can think about the affine line, which has coordinate Z, okay, which is a neighborhood of 0 and contains every point except for the point at infinity. Or you can remove the point 0, so to speak, from this P1, and that's the affine line which has coordinate Z inverse. Okay, and one way to actually prove this is that it turns out that there's a non-constant map from X to P1, and what you can do is you just look at the inverse images of these two open sets, and that will give you an open affine cover. Okay, so let me just give you a picture for why this is true in the simple case where you have some projective plane curve, like something that looks like this, for example. Okay, so what you can do is that you can pick a point inside the plane. So here you're inside the projective plane, and you have this blue projective curve inside here, and you pick a point away from it, and you just basically project away from this. Okay, so that means, what does that mean? Okay, so what's your map? So remember, the projective line is equal to the set of all lines through this point. That's one way to think of the projective line. So if you look at a line like that, that's a point in the projective line, and you send these 3 points to this point of the projective line. Okay, so let's suppose you can always think of this as saying by changing coordinates on P2 as, for example, being one of the coordinates being 0, and this is another one being another coordinate equal to 0. Okay, so maybe this is inside here. You can change coordinates, so this is X, Y, and Z are the homogeneous coordinates. And you can remove X equals 0 and say Y equals 0 here. And so the complement of this X equals 0 is an affine plane. And so the complement of the blue curve there is an affine curve. And that's going to be one of your open sets. And then the complement of Y equals 0 is going to be another affine curve. And that's going to be your other open affine set. Okay, so it's quite easy to prove it in this case of a projective plane curve, and actually if you have curves in higher dimensional projective space, you can do the same trick. Okay, so this is a rather interesting fact and a useful one, and we'll use this in our setup of cohomology for quasi-coherent sheaves M on X. Okay, and now we're going to pick any open affine cover of this X, which has two open affine sets in there, U0 and U1. And what we consider first is the following map, which is going to be quite useful for us. Okay, firstly, we look at the sections of M over the two open sets U0 and U1, look at the direct sum of this. And then we also look at the sections of M over the intersection U0 intersect U1, which I'll denote by U subscript 0, 1. Okay, so of course, when you go from U0 to this smaller open set, there are restriction maps, so you can restrict via row 0 from U0 to here, and via row 1 from U1 to this intersection. And what we'll do is we'll map from here to here by using this restriction here and the negative of the restriction here. So in other words, that if you get sent to 0 here, okay, that means that the restriction of row 0 is equal to the restriction via row 1. In other words, these two sections, they agree. So there's 1 over U0, 1 over U1, they agree on the overlap. And so by the sheaf property, what does that tell you? Is that the kernel of this delta is precisely just the global sections of this quasi-coherent sheaf M, which would denote as usual by H0 of M, or if you want to emphasize that we're working over X, it's H0xM. Okay, so this is independent of what this open affine cover is. So our working definition involves Čech cohomology, and we're going to define the first Čech cohomology, or first cohomology of this quasi-coherent sheaf M. So this is H1M or H1xM, and it's just going to be, instead of the kernel of this map, the co-kernel of this map. Okay, so it's this the sections over this intersection modulo the image of this map here. Okay, that's a co-kernel of this. So this is a working definition. It's a very good one to understand what's going on. Theoretically, it's not quite so good because it seems to depend on the choice of this affine open cover. Okay, but it can be shown that in a sense it's independent of this choice. Okay, so some things to note about this. So firstly, this H0, of course, we know is a functor, and this H1 also is a functor, and we'll see this shortly. Okay, so why have I set things up this way? So the following sort of explains and gives some motivation for why we've made this definition, and this is a useful one. And that's the long exact sequence that we get in cohomology, which is something that we expect from cohomological theories. And I want to show you how it arises in this case here. So now suppose we have a short exact sequence inside this category of quasi-coherent sheaves on X. Okay, so there'll be 0 to M prime to M double prime goes to 0. Okay, so what does that mean? So that means that if you look at any affine open cover or affine open set, okay, and look at the sections there, you get an exact sequence. So if you look on just U0, okay, you get an exact sequence 0 to M prime U0 to M U0 to M double prime U0 to 0. And you can take this direct sum of that exact sequence, short exact sequence, with what you get when you look at the sections over U1. Okay, so there's some exact sequence there like that. Okay, so you can also look at U01, which is also affine. Okay, and so you also get an exact sequence when you look at the sections over U01, the intersection, because that's also affine. You get an exact sequence like that, a short exact sequence like that. And then you get morphisms that are defined via this restriction maps. Okay, so there'll be the positive restriction on the U01 to the intersection, and negative of the restriction on the U1 to the intersection. And you get three maps corresponding to this delta, delta in the middle, delta prime to the left, and delta prime on the right. Okay, so remember the kernels of these maps will just give you the global sections of these three quasi-coherent sheaves. And the co-kernels of these maps are going to give you the H1s. So this is why we get functoriality. If you have a morphism, say for example from M prime to M, and now that can be arbitrary, okay, of course you get a corresponding morphism on the co-kernels. Okay, and the point is that here, since we've got a morphism of short exact sequences, you have the kernel co-kernel sequence, and that's a long exact sequence by the Stank lemma. Okay, so let's just write down what that long exact sequence here is. So the sequence of kernels is just the H0s, and that joins on by the connecting homomorphism to the sequence of co-kernels, which are the H1s. Okay, and this is the important long exact sequence that we have in the case of cohomology of quasi-coherent sheaves on this quasi-projective curve. Okay, so let me just say some words about why this is really interesting. Okay, so it takes a little while to work through all the implications of what this means, but the main thing here is that remember we talked about the problem of lifting global sections. Okay, so if you have a surjective map like this one here, M to M double prime, okay, we want to approach the question, okay, when can we lift a global section from here to here? Okay, so in other words, an element of here, when does it come from here? And we can see, by the way, from this setup that this is, you'd expect this not always to be surjective, because you have this kernel-co-kernel sequence. Okay, this kernels, this sequence of kernels, you can only expect to be left exact here. Okay, but the point is that, well, to say that it comes from here means that it's in the image of this, and since it's exact, that means it's in the kernel of this. So the obstruction to being able to lift something here to here lives inside here, so it depends on whether it gets sent to 0 or not. So understanding this H1 of this M prime is very important. And in general, trying to understand H1. Okay, so the first thing is that why is this first Čech cohomology useful? This first cohomology. H1 is useful in the problem of lifting global sections. Okay, so let's see whether, you may think, well, how much information can you get about that? Well, the typical approach that we're going to use is the following one, okay, which is very, very important. So I guess in general, one thing you want to know are what are the dimensions of these global sections, okay, the spaces of global sections. Okay, what are the dimensions of them? So more generally, you denote, given a quasi-coherent sheaf M here, little hi to be the dimension of HIM. Okay, so you're interested here in little h0, okay, but we've also defined here little h1, okay. And the point is that, well, little h0 and little h1, they may be a little bit hard to control, okay. But what is easy to control is what's called the Euler characteristic, which is the difference of these two. So this chi of m is defined to be h0 of m minus h1 of m. Now, of course, in general, there's no reason for these to be finite numbers, okay? But Sayre's finiteness theorem, which we'll look at in a later video, which says that in the case of a projective curve, okay, and the case where m is coherent, these will be finite numbers, so you'll get a finite number here, okay? So in the case that this is a finite numbers, okay, what we'll find is that we have this wonderful formula here, which we call additivity. The Euler characteristic of m, the one in the middle, is the same as the sum of the Euler characteristics of the outside ones. Okay, so this is called additivity. Why? So you can think of this m as, well, it's got a submodule of this form, and the corresponding quotient is m double prime. So it's kind of built out of these two. So the typical situation that you get here is if m is actually the direct sum of these two, then you get such a short exact sequence. Okay, but this is a bit more general. And in that case, the chi of the middle is just the sum of the chi's of the outside. So it's additive like that. Okay, so this is rather nice. And this is quite easy to sort of see why this is true. And this follows also just from this long exact sequence here. Okay. So let's have a look at this long exact sequence and see where we get this from. So this is just a long exact sequence of vector spaces, and let's suppose that all the dimensions of these vector spaces are finite. Okay, so the nice fact about this, and this is not difficult to show, is that the alternating sum of the dimensions of these is equal to 0. Okay, so this is a good exercise that you can show. And it just follows from the fact that if you have a short exact sequence of vector spaces, finite dimensional vector spaces, and the dimension of the middle one is the same as the dimension of the sums of the outside ones. Okay, so you can split this up, splice this, or split this into a sequence of short exact sequences, and if you apply that several times, you'll see that this is true. And so what do you see here? So basically, if you look at the alternating sum, you get plus this, minus this, plus, so maybe I'll put some signs in here, plus this one, minus this one, plus this one, minus this one, plus this one, minus this one. The dimensions, you get 0, so it's plus minus here. You'll get, I guess what we can do is we can prove that 0 equals chi of m prime minus chi of m plus chi of m double prime. So you've got plus minus, that's chi of m prime here. You've got minus plus here, which is the negative chi of m there. And then you've got plus minus, which is the chi of m double prime here. Okay, and that proves for you this wonderful formula. So this allows you to do a lot of induction arguments. Okay, if you want, you can break up this m into a subsheaf and a quotient sheaf like this. Okay, then you can break this up and you can compute at least the chi from the constituent quotient and subsheaf. And that allows you to work very nicely with something which becomes fairly numerical. Okay. And the final thing is that actually you only really get anything interesting if you're in the projective case. Once you're quasi-projective, you're actually affine. And what happens when X is affine? Well, in that case, you can assume that your open affine cover will actually X is U0. Okay. And then once X is U0, then what's U1? Well, U1 is also the same as U0 is L whole of X, right? So this is the same as the intersection. So you have U1 equals U01. So when you look at this delta here, well, this U1 is the same as this, so clearly this is already surjective, so the co-kernel is 0. Okay, so H1 is 0 in this case. And that's kind of what you expect, because in the affine case, okay, so really what is this category of quasi-coherent sheaves? By definition, it's just a category of modules, okay, over the corresponding coordinate ring, okay? And so, of course, exactness is defined in terms of that category. So really, you don't have any problems with looking at global sections, okay? So the global sections actually preserves all the information that you need. I want to conclude this video by showing you what happens when you look at the cohomology of torsion sheaves. Okay, so let's just recall firstly what is the torsion coherent sheaf on a curve X. So let's suppose T is such a sheaf. Or one way to think about this is it's just a sheaf which is supported on a set of points. Okay, so its support is 0-dimensional. If you look at the structure theory of such coherent sheaves on curves, you can write it out in a slightly different way, and that's the form that we want to use here. Okay, another way of writing this out is that you have some filtration. Okay, so there's a sequence of subsheaves, coherent subsheaves, T0 equals 0, T1, T2, all the way up to Tn, such that if you look at the successive composition factors, so Ti plus 1 over Ti, they're all isomorphic to skyscraper sheaves. So this is isomorphic to OP for some P, and that P, of course, can change as you vary which way you are in this filtration. Okay, so what's really nice is that once you have such a torsion coherent sheaf, actually it's true also for quasi-coherent sheaves too, but let's just look here for torsion sheaves, you will have the H1 is equal to 0. Okay, so that's rather nice, and it's a very useful fact as well. Okay, and I want to show you that basically we have the technology to prove this, and it's quite easy. And the way we'll do that is we'll just use induction. Okay, so the case we'll use induction on this set of torsion sheaves here. Okay, so I guess for I equals 0, we're okay. And let's prove it for I plus 1, assuming that H1 of Ti is equal to 0. Now here, this isomorphism gives you a short exact sequence. Ti embeds in Ti plus 1, and the quotient is OP. So we get a following, a corresponding long exact sequence. So let's just look at the H1 part of that. H1 of this subsheaf Ti maps to H1 of Ti plus 1, and that maps to H1 of the quotient OP, and that goes to 0. Okay, and what you want to show here is that this here is going to be equal to 0. Okay, so well, we're going to assume by induction that is equal to 0. So that means that in fact, once you have this, that these two are actually isomorphic. So you just now have reduced to the simple case where you need to show that this is 0. In other words, the H1 of some skyscraper sheaf is always equal to 0. Okay, so let's just remind ourselves what this skyscraper sheaf looks like. So if you work over any open set U here, what is OP of that U? Well, it depends on whether P is in that U or not. Remember, the support is just that P. So if P is not in U, then you get 0. But if P is in U, then the sections of this OP of that U is just your K, if K is algebraically closed, or in general it's just that residue field. Okay, so this is a complete description of the sheaf. Okay, and now what do we have to do to compute the cohomology of this? The first cohomology, we use this open affine cover. So you write X as U0 union U1. Okay, and U0 and 1 is intersection, and we have this map here delta. And we want to look at the co-kernel of this. Okay, so the kernel, remember, gives you H0, the co-kernel gives you H1. And the point is that, well, P has to lie in either U0 of U1, since this is an open affine cover. So you'll get K in one of these two. And of course, this may be K or 0, but either way, it's either you get the identity or negative identity, or you get the 0 map. Either way, it's surjective, and that shows you that H1, in this case, is equal to 0. So H1 of torsion sheaves is actually equal to 0. Okay, so that's a rather nice fact. And this is a special case of what's known as Grothendieck vanishing. Okay, so here this the support of this sheaf is 0-dimensional, and so the only cohomology you get is up to degree 0. You can have h0, you can have global sections, but h1 is 0. Okay, so on a curve, one of the things that we saw, we introduced h0 and h1. We didn't introduce higher ones because when you go to the general definition, h2 is also always 0, as is h3 and so forth. So this is an example of Grothendieck vanishing. So in this video playlist, I wanted to talk more about cohomology, and the next thing I want to show you about is this rather interesting finiteness theorem, which says that in the case of a coherent sheaf, if you're working on a projective variety or projective curve, you always get finite dimensionality of both the global sections and H1. I hope you enjoyed this adventure in pure mathematics.